Welcome to proglangcast. This is episode 14. My name is Christopher Augustus.
I'm Steve Thames.
Today is a revisiting of Bye Bye Hello World in BQN, the array language.
Right.
Just like the scheme that I did, the first BQN, it has global variables, it has mutation, and so the point of revisiting was to make it immutable. I have achieved that. Let's switch to the source mode.
And this is BQN.
We've already introduced BQN, kind of a half episode. It started as APL and then went to BQN. This was the original first attempt to code Bye Bye Hello World, our spec, in BQN. Over the last week, I have hacked at this quite a bit, and I now have 6 more versions of this code. So you're going to notice that it says BBHW-mute. No longer the idiomatic version. This original one is now the mutation version. Something to know about the language BQN. It was inspired by APL, created by Marshall Lochbaum. There's a C implementation from Zyma, which is what's being used here. It's essentially Marshall's evolution of what he feels like an array language can now be after years of working in APL and J, and his knowledge of other languages as well. It's an array programming language. The syntax is unusual in that it includes these funny glyphs in here that requires Unicode support and editor support or copy and paste support. It's like APL, it's not exactly the same symbols. But rather than walk through this because we've seen this before, I'm going to immediately step to the new version, which is now what I think is the most idiomatic. It looks like that. In Vim, actually, if you say help BQN, because I added syntax files that Marshall provides on his site, it gives you a little help screen. And in that, they give you copies of all the symbols. And they actually show you the keyboard that you can strike. You can use a backslash and you can get the symbols. But what I did is I just copied them here into the comment at the top of the file.
Back in the day, of course, we had APL keyboards. Later on, when we were trying to do that with other keyboards, I had to do that in a number of languages. It's just easier to copy the symbols over.
So let's pop back to the previous one. Look at the bottom of the code. You can see it's mostly the same, right? From the term out raw world hello, this looks pretty much the same. In the original source code at the very beginning of the code here, 2 global variables are created and assigned values. The first is count, which is assigned a value of -1, which is obviously not going to be valid later on. And then we have a global variable called input, which is immediately assigned to the command line arguments coming in. Then we have a while loop that is going to look at the input that we've gotten already. If there are input arguments, if it's something there, it's going to immediately try to convert it to a number that's valid. And if it's not, it's going to give an error saying this is invalid. It's going to ask for a new countdown, and that's inside of a while loop that's going to repeat until it gets to a valid count. The top of the code is essentially that. We do have this variable called input, but as you can see later on, input doesn't matter. All that matters is that we get a good count variable, and then the last 4 lines is where we actually do the output. We output world hello. Whatever the count is, we repeat that number of times, printing a second, flushing it, and delaying a second. The mutation that's significant here is the first 2/3 of the program at the top.
Right.
How do we get a valid count variable from either the command line or from the user providing input? But once we've got that, no mutation is required. It's all constant values with the count outputting to the display, right?
We've got 2 global variables, count and input is going to be taken from the command line. If that's not good, then it's going to be taken from a prompt, and it's going to continue to do that until it's valid. And then the final valid value will be assigned to count. And that's what we use to do the world hello and then output every second, count times. So both input and count are your mutable targets here. Input is going to be mutated multiple times, and count looks like it's only going to be mutated once.
Count gets initialized at the very beginning. We don't really consider the initialization of a variable to be mutation because this is the first time any code is going to see it. So for all practical purposes, it's a constant value.
Its initial binding is -1.
But it does get changed below. It gets reassigned.
That particular arrow symbol, the one with the little curly tail on it, is that an assignment?
BQN has 2 assignments. The initial assignment is a straight arrow pointing left, And you can't have a variable that's uninitialized. In fact, that's how you define a variable, is you give it a value. It's not like C, where you can say I have a variable X that's not initialized. And then when you want to assign a new value, BQN requires you to use this bent left arrow. You can't use the straight arrow. You can only use that the first time you initialize it. So it does have a symbol that does clearly say this is mutation. In our original code here, we see it in 3 places. Count gets reassigned once and input gets reassigned twice. One of the great things about BQN is the documentation. There's just so much of it, and he goes into so much detail and everything. There really is an answer to every question. The left arrow is called define, so let's take a look at that. Defines a new variable with a name and value v.
Must not already exist.
And now the bright yellow is called change. Leftward arrow with the hook changes the value of a variable with name to value v. Variable n must already exist. He makes a pretty strong distinction, I'd say, by the fact that he's highlighting that in the bright yellow, saying, this is a mutation here. Okay, so this is the new code.
So what's different here is you've changed the mutable portion, where we're taking the input value and validating it and converting it to an integer.
We still have a count variable, very first thing at the top. We're assigning it now to an entire expression in which there's no mutation inside of it. It's completely functional. In a single assignment, it's going to do everything that we did before. It's going to try to get it from the command line. If it's not there, it's going to prompt for it. It's going to do validation inside this expression. If you do it incorrectly, it's going to give you an error and ask you to do it again. And all that's going to collapse down to the single initialization of count. There's no longer an input variable. You'll notice that one's gone. So originally in the previous code, the count variable was named 3 times, and the input variable appeared 1, 2, 3, 4, 5, 6, 7, 8 times. In the new code, there's no longer a need for an input variable. It's completely gone. And count only appears twice. It appears when it's initialized, and it appears when it's used. What do you think of that?
You should be reading this right to left.
That's right. And because there's a block here,
I see it now.
there's 4 lines here, or 5 lines, which make up a single expression using the open brace and the close brace. This is the only way that you can expand a single expression across multiple lines. You have to use a block, an open brace and a closed brace. Otherwise, a complete expression must be on a single line.
I read it right to left, and the while loop starts at the bottom, not the top.
And in fact, something happens even before the while loop. So if you read it from bottom to top, right to left, what do you see the very first thing happening there?
That we're appending args to an empty string, then taking the second position argument, and then we are taking that value to this one that's going to check it against digits to make sure it's an integer. And it's going to do this while it's not digits. Then it's going to do this get line countdown, and then the result of that is going to be piped back into this test at the top. It's really different. Now that I've remembered to read it right to left, now it makes sense. And then finally, the result of that, when it comes back and is valid, then that's going to be assigned to count. And somewhere in there, I'm assuming that the string input is going to be converted to an integer. I'm not exactly sure what symbol is doing that, but I can visualize what it's doing now, even though I don't understand all the symbols.
I think the most important part of this 5-line expression is the while. And this is where it feels like when you're doing array programming, you run into the sandbar a little bit, is when you're dealing with control flow. Array programming is really great at doing mathematical transformations, numerical transformations, taking bodies of data, manipulating them, reshaping them, applying operations on them, parsing them. But when it comes to the imperative aspect of the code, it feels not quite as comfortable as we are in the imperative languages. Here, I am using the system function while. We know that because it has the solid dot opening, and then it's underscore while underscore. So this is the only thing in a loop form in BQN that guarantees tail call elimination. In BQN, Marshall does a good job of documenting that. He has a whole section in his documentation that talks about how to do equivalent control flows, how to do whiles and do's and ifs and case switch statements using the constructs of BQN. But he does warn you, he does say, we don't do tail call optimization or elimination unless you use this particular while function.
That's the only one that supports it.
It's the only one that supports it. recursion to the same function will eat up stack, no matter if you call yourself properly at the end. So there is no TCO, and I'm using specifically CBQN. It's possible maybe at some point they may add that, or another implementation would provide that. But at a minimum, Zyman, Marshall, and CPQN say, here's how you'll get tail call elimination. Use the system function, and you won't have a problem. You won't run out of stack. So let's look at the previous code. We have the potential of infinite looping, right? If the user enters the wrong thing, assuming they don't die of old age, they could just keep entering wrong things, and it's going to continue to loop, potentially eternally. We don't want to blow up the stack. So we used while originally. We're still using it. What do you notice about the way it looks?
Well, this reads much better left to right. When we were first looking at it a few minutes ago, I, of course, didn't remember that in this language, you want to read it right to left. In the new one, the latest one, you can't understand it all unless you understand you have to read it from bottom to top and right to left.
The way that I coded it here was based on an example that Marshall provides in his documentation of control flow. That's what he says here, reinvent control structures. He's got a whole section on that, control flow in BQN. And he specifically says, okay, it does not have the Algol style control structures that we know of in what 99% of languages program in. There are equivalent expressions. There's an if, repeat, if else, chained if else, switch case, loop forever, and there we get down to while. He gives an example of structuring it in such a way so that it looks, like you said, left to right. While some condition, here's a block of code to execute it. Maybe a little misleading to people not familiar with BQN. There's kind of a trick here to the way this does this so that you can structure it that way.
Those people are represented by me.
It's not necessary to do this kind of funky thing here where he's got two direct function declarations appended to a list and then passed to this construct. This is what's kind of weird. You can use the while down here. This is where he talks about the tail call optimization. We have this special system function which will take care of that problem for you. He also says there's other ways you can not have to worry about it so much, but if you want to guarantee that you're not going to burn out stack, you're going to use this. But we don't have to give it this shape. And I chose not to do that to keep a more BQN look to it. So I'm still using the while, but instead of appending a couple of functions to a list and then doing a reduction over the list, which is what this kind of thing does here, I just went for, as you say, right to left evaluation. All right, so I added a little line here kind of as documentation. This may help you read the expression above here with the while. You've got the solid dot while system function. On the left, it expects a function f. On the right, it expects a function g. And then it requires an x argument. So you got to have an f, a g, and an x. And then the w is optional. In the expression above, where count is assigned, there is no w. So we have just the x. A function starting at the second brace here, matched here. So that's the f. Because it's a big expression, I made it on 2 lines. So I wrapped it in a block. But this is a single function. The G fits on the line with the while. It begins at this paren and ends at this closed paren here. And then the X matches the input to the while, which is our expression that grabs our command line arguments. So is that easier to read a little bit?
No, absolutely not. I mean, I understood all of that before you showed the little helper.
The helper didn't help.
It doesn't tell me anything I didn't know. I can see where the individual functions are. I am curious about the W, though. The X is coming in as that second element from the command line arguments. And I can see what the G is. That's the function that is checking the validity of the command line arguments. Then the F is where it's handling what happens if it's not valid. So what's the W in this case?
The W doesn't exist here. I just put it in to show you that if you wanted to have a W argument for a while, you could put it there. X is the initial argument to the first time G is called. G is going to produce a 0 or a 1. If it produces a 0, we're out of here, nothing happens. If it produces a 1, F is executed. The result of F now becomes the new value of X for the next execution of G. That is critical for this while, and I'm glad they implemented it that way, because I was trying to structure it and I thought, okay, I got the initial argument to G. How do I get subsequent arguments to G without using global variables? Am I going to have to set a global variable and then read a global variable? And he's like, no, we do this in a functional way We're going to take the result of f, the block that you want to execute in your loop, we'll make that the new input to the condition.
That's intrinsic mutation. It's not an assigned variable, but it is an assigned symbol, and that's being mutated.
No, it's new value being passed into a subsequent invocation of G. That's functional.
I understand, and I agree with that. I'm just wondering how it would look to someone who comes from an imperative world. They would respond by saying, well, there's mutability, that's X is being reassigned. And you're right, it's not, because it's another invocation of it, so it's not mutability.
Mutation is if something you're holding on to changes while you're holding on to it. That never happens anywhere in here. There's nothing you're holding on to it for while the time you're able to deal with it, access it, or look at it, it's going to change from one value to another. Some new thing got created and passed to a new instance of an invocation of a function, but you're not holding on to that.
The output of f is being piped as the input to the next recursion of that function that's executed by the while. And because the while has TCO, you're not going to run out of stack. You could run that a billion times. It'd keep running happily along.
That's exactly right. It took me a while to figure out how to structure the while. It was easier to make a recursive version, and I did that. I got rid of mutation, I got rid of input, but I had a recursive call, and I knew I've got to get that while working because this recursion is going to burn out stack eventually. Yeah, I don't know that we need to go through the details of this. It's the same thing we saw before. Again, we do have to read it right to left, top to bottom.
Bottom to top.
From the end of the block towards the beginning of the block.
You could do it all in one line.
It's funny you could say could because you're going to see that.
Oh, really?
Yeah, you're going to see the one-line version. We don't need this little helper anymore, right? So let's go back to the original code.
In the initial assignment, count left arrow dot BQN. What is the significance of that construction?
BQN says whatever argument you pass to it is BQN source that I will execute.
So everything that comes after the BQN is the BQN source that will be executed and then assigned to count.
This is the trick pointed out to me by Adam and APL that I should have done in the first APL version, which is how we convert a string to a number. So if you give it a string that has a valid number in it as an expression to the interpreter, it'll give you back the actual number. And because we're guaranteeing that we're building up a string that is a valid integer, but it's still a string, I can't loop on this string. See the count down below here? I have to turn it into an actual integer. BQN is the way to do it. In APL, we use the little fire hydrant, which is called execute. Same thing. We give it a string because that's what the interpreter does. You type in a string number and it gives it to you as a number. In Scheme, we called the function string to number. Our while expression is the whole thing to the right of that. We basically build up this valid string. That becomes the right argument to BQN. The result of that is actual count, and it only gets initialized once. So we've achieved it. We are using a global variable here.
It's just been assigned once.
True, it's a global constant. And I felt that this would probably be more idiomatic. Marshall himself doesn't seem to be very extreme about tacit. He definitely recommends kind of using it in the small, not using it so much in the large. And I've gone through quite a lot of the test code and example code in BQN, and I'm trying to match the style of the way they do things.
Well, I would absolutely agree with him. Doing it in the small is the way to go. For one thing, that's real clarity there. If you do this in a fully tacit version where you're not going to have any variables at all, well, yeah, you can do that, but it's going to be a lot harder to see the segmenting of the code into step 1 and step 2.
So the hard part to read, I think we can agree, is the beginning. But from top to bottom, we are kind of following the flow of the program. When you look at the actual outputs, they kind of read more from left to right because we are using this diamond, which gives us separate statements. We see the flush occurring after the output. We see the delay occurring after the output. If you ignore the first part where you have trouble, like you said, you've got to read it bottom to top, right to left. But if you could just take this as a black box, you could see this as straightforward procedural description of what's happening in Bye Bye Hello World.
What's the little diamond?
Unfortunately, this font makes it really hard to tell, but this is a diamond.
The statement separator?
Yes, it's the same as the diamond in APL. It allows you to put multiple statements on a single line. Otherwise, without the diamond, we just have to put it on the next line.
We're not always reading right to left.
We interpret statements from top to bottom, and then on a single line, if there's multiple statements, they're interpreted from left to right. the expression within a statement is parsed from right to left. So that's what's confusing. We go top to bottom, left to right for each statement, but within the statement, it goes from right to left, and if there's a block, it's just going to execute the top line of the block first. So there are statements within the block.
So I've got a block going back to where we're assigning the count all the way out to the end. An array containing one empty string, we're appending that to args. I see the not left parenthesis. What is that symbol? It looks like a left angle bracket, but it's not exactly.
This is a unique glyph in BQN. This is one thing he provides that's an improvement over APL. When you want to create arrays, just declare them with literals, they do stranding. If it sees a bunch of literal values separated by white space, it says this is the attempt to strand an array. Because that creates a lot of problems, and I think you described that in the documentation you read, where he talks about stranding being an issue. In BQN, he decided there's two ways to create lists. One is using the little smiley character, so you can glue things together. The other is you put them between these two kind of angled brackets, but they're not the same as normal angled. They're taller, and they are a Unicode glyph here.
Okay, so that is an array of one element of an empty string. And then we've got this kind of curly tilde, which is appending the empty string to args. And then what does that, the little two dots mean?
That's a modifier called each. Whatever function is on my left, I'm going to apply it each time to the elements of an array on the right.
And what's the line with the little circle on the end of it?
That's a combinator.
Concatenated to it? Is that what that's doing?
Yeah, I'm going to show you. If I take this out, if I get rid of that, and I read this, it is saying for each element of args, concatenate them together to a single element. Now, if I want to put a separator between the elements, this is partial application, giving an argument already to that function, creating a new function so that it always has this left argument, which is this blank, and then reapplies that function to every single argument. So I need two arguments, and I'm doing it each over an array, so I'm grabbing the two arguments from the array. I'm taking the first and the second, appending that. This way is saying, no, I don't want you to do that. I want you to use something else as the left argument every time, and only grab the right argument from the array.
Your args array is not going to have parameter 0 as the name of the script?
No. Invoking BQN only passes the actual user args that were passed.
And args is always going to be a list. And if it's empty, then that's going to be an empty list appended to that list. What's going to happen when you take element 1 when there's no argument?
Before we get to the downward arrow, which is called drop, we have a single string.
So that list has all been concatenated into one string.
Correct.
And you're dropping the first one because you expect there to be an empty.
Because of the way I concatenated the spaces, there's going to be an empty space at the very beginning. And so if there were no arguments, I am appending nothing to a space. At a minimum, I'll have a single space. So what happens is I get rid of the space. If that was all there was, I'm left with an empty array, which is what I want.
So if args has 1, 2, and 3 in it, and you join it together like this, it's going to be space 1, space 2, space 3.
Correct. It's actually not join. It's prefix each element with a space. Yeah.
That little symbol, that line with the circle is saying you're going to append each element of arg to a single character string, not append the single character string to each element of arg. It's reversing that.
Yes, because I'm pointing to the left, and I'm saying the left argument is this, the right argument is args. I want to point out, though, on this version to note, there's only one use of an actual embedded function, which names its parameters. The little double scored X being used inside a direct function. These other blocks are not functions. These are evaluated immediately. It's just the blocking structure to allow you to have the expression span multiple lines. So it's not a function unless you actually put an argument name inside of it. All right, so let's go on to the next. I think you'll like the next one. Recognize that. The file is named BBHW-sub-func. This is subdividing the whole algorithm into separate functions. Every single thing we do has been made a full function. You can see that. Every one of these is with the open brace and closed brace. And it either has the argument names in it, like the double score X. I don't think I use a W in here anywhere. If you never refer to the x, but you still want to say this is a function, not immediate expression, is you put the capital S at the top. It doesn't get evaluated until the function is actually called or used, right? So every single one of these is a function. This pretty much matches the scheme one that I did. I tried to use the same names.
Is there a significance about the S being capitalized?
Yes, it's self. If I put it here at the end, this is a recursive call to itself. But at the beginning before the colon, this is a function header declaration.
If you took the S colon off the front of it and you left it just the way it is with the capital S at the end, then it would still be a function.
Yes.
And if you executed it, then it would just keep executing itself over and over again.
But I don't want to execute myself.
No, of course not. And you need something to say that this actually is a function. So that's why you put the S colon.
And that's the function header. This actually tells you the signature of the function. S is the name, and there's no arguments on either side. If I put this in there, S is a monadic function that takes one argument.
Can you specify multiple arguments?
Yes, I can put the W in there if I want. We don't need to talk about headers. The important thing is to know that without any arguments, I have to give it a header to make sure it's a function. So this is what you were saying, declarative. I'm declaring all my functions. I'm not executing anything in here. Nothing gets evaluated. It gets parsed. It gets built up as function implementations with names. And then the single line at the bottom is the execution of the whole program. And we did it the same way. We read it in English, get count, say hello, count down, say bye-bye, exit. And notice I specifically used the diamond so that we could read it all on a single line, reading from left to right. It looks almost identical to the scheme. So this shows you that BQN, you can code very much in a Lisp-like functional style if you want to. It doesn't use parentheses like Lisp does. But we saw that in Marshall's documentation. He said Lisp was an inspiration. This is almost equivalent. What do you think of that?
Well, I like it. I would change some of the names, like SaySec. I don't understand what that is.
Say second.
Say second.
I originally put second in there, but it made all the names much longer and made my thing go out. So I was like, sec is second. Yeah, you could defend this. SaySecSleep. That's a little bit better. Now we're talking about natural language being important because English versus...
And I would change valid input to is valid input.
You like using the is's. I don't like using the is's.
Is only digits or is valid input.
I say only digits. I say valid input.
But those are tests, right?
Yes.
Okay. So I would have done an is on those just to delineate that they're tests. Because otherwise valid input could be something else. Only digits could be something else. Only digits could be the string of digits rather than testing for is it digit.
It's a personal preference. I don't like using is. It's passive speak.
It's not passive if it's interrogative. It is passive if it's declarative. If you're saying something is something else, then that's passive voice. But if it's interrogative, you're not.
Well, when you write yours, you can name them however you want, which you did in Erlang, in Elixir.
Damn straight.
So the subdividing is somewhat arbitrary.
Ask while bad is interesting because I might have changed the name there, but I love the way it reads. Ask invalid while valid input.
Well, not valid input. Yeah, that little not.
That's incredibly readable. You have declared your functions so that you can almost read it like English. This is what you would like to call self-documenting. Thing I was talking about before about validating the input and seeing that it's going to take in. I don't need to do all of that because it's telling me that right here in English. And that was my whole argument about, you're talking about, yes, if you're laying bricks in one language forever, then absolutely, you're not going to have to know. You're going to see exactly what it's doing. But in my experience, if you're working on a larger canvas than that, then you may not work on those languages and just lay bricks all the time.
Well, one of the things I'm hoping that our audience appreciates is that you and I have very different points of view. And so they get to hear the defenses used from the different points of view. If you and I were in lockstep, thought the same way, and we had the same priorities, same preferences, it'd be pretty boring.
Yes, it would.
It would just be this mutual admiration society. So we tend to agree on some things. I think in terms of like our philosophy about some of the ills of software, we probably agree on. When we get down to kind of the details of how we would do things, there's a lot of differences. I'm not going to make the argument for what I like more here because we're just already getting derailed. So we'll come back later. Oop. What did I do? I renamed it.
You followed some good advice.
I followed some good advice. Yeah. I prefer to read this. But I'm doing this for all the implementation so I can show these different points of views. I consider this not to be idiomatic. I would think that BQNers would think, okay, yeah, that's nice, but that's pretty wordy, it's pretty verbose. You can see what's happening in one line from a black box point of view, from an abstraction point of view. Get, count, say hello, countdown. But how does say hello work? Okay, I have to go find say hello. Okay, it does this. All right, that's pretty straightforward. How does countdown work? Oh, well, countdown does this, which calls this, which calls this, which calls this, which calls that, which calls that, which is somewhere in here, which is somewhere in there. If you look at the previous one, you can see in the order of execution, not only what's happening, but how it's happening. This declarative approach definitely is under the philosophy, separate the what from the how. At the top, most abstract level, we don't get into how at all. This is what. We don't know how it's happening. And at each stage, we see a what, and the how is deferred to somewhere else. And then we look at that how, and that is a what that's deferred to someone else, until you get down to the primitive of the languages like trim blanks. I could have made this actually call two functions, right? One called trim leading and trim trailing. This actually combines both into a single. And this came out of, by the way, the BQN crate. So if I wanted to break it down even further, it would be a succession of abstractions and implementations of those abstractions, and then implementations of those abstractions, and then implementations of those abstractions until we get down to the...
And it would be going overboard.
Right, which is...
You could have just called it trim, and that would be standard with the imperative languages like C, JavaScript.
Well, yeah, but...
Trim trims both the beginning and the end.
Yeah, but trim what? Trim blanks. I said trim blanks because it's not trimming carriage returns or tabs or anything else. It's specifically only trimming a blank character.
Oh, okay. Well, that is important then. It's not trimming white space.
Exactly, right. I would say trim white space if that's what it was doing. So as you can see, the choice of names is subjective, and the choice of the separation of abstraction to implementation is subjective. I broke it down into what I thought were the pretty recognizable pieces. There's some reuse in here. I think not empty is reused. There you go, 3 times. There's dry right there. In other cases, used once. This could have been embedded. Could have said, yeah, not empty and only digits. I could have put that directly in here. But as you point out, the purpose of this function is to comment what it does.
It's all a matter of balance, right? It's a judgment call. In this particular case, I think it makes sense.
And that judgment is driven by priorities. The priority of this code was separate abstraction from implementation. It's a judgment call, but that's the purpose that it serves.
Well, what about SaySec, for instance? I wouldn't have done that. I would have just done the SaySecSleep since it's only used once.
You're right. It's a judgment call. I said, say second and sleep. I could have done this. I could have just put the delay at the end.
Was the whole thing. We just count it down.
And there's an example right there. I just got rid of it. I just said, look, let's put SaySecSleep. One of the things I want to point out about this, regardless of the fact that it's very subdivided, you'll notice a couple of nice things about it. There are no intermediate variables. Right? All the arguments are named, but there's no count, there's no input. These are all functions. And in the final statement that executes the whole program, no intermediate variables, no globals, no mutation. This is still immutable all the way through.
On that last line, it's looking like it reads left or right.
I wanted to be tricky.
That's why you're using the little line with the circle in it.
This is called before. This says call get count before the thing on the right. It's going to evaluate it from right to left. It's going to see this block, but it's attached to a before. So it does get count first. Then it evaluates this, and inside there it says, do you say hello before countdown? Otherwise, it would execute countdown first because it's going from right to left. Take the argument that was W to the whole expression, which came from get count, and make it the X argument to countdown. This is the way that I throw the argument from get count over hello. Remember I did that in Scheme? I made this tricky little combinator called after. Actually, they have an after in here, but in this case, they're using one called before.
Maybe none of this is idiomatic, but that last line is definitely not idiomatic.
It's not idiomatic, but the whole purpose of this was to create a fully left to right reading abstraction that follows the algorithmic logic of the program without using an intermediate variable. If I don't do this, I have to assign get count to count, and then I have to pass count to countdown.
What's the @ symbol? What's that about?
BQN does not support what's called a nil-adic execution of functions. You have to give it a right argument no matter what. The left argument's optional.
The @ symbol represents the right argument.
It's a way of saying X is nothing, but I have to give it something or it won't execute.
Isn't there something like the last term of say hello being the X? Isn't that going to make it the output?
I thought about that. I could have passed X into say hello and then passed it on through.
Pass through a variable that I'm not going to use? No, that's not something you want.
Probably would have done something like make a separate function called say hello, pass X. I could do that, and then down here I would say hello, pass X. I could put the exit and the say below, make it all one statement without the diamonds. But now we'd be reading it completely from right to left. It'd be like get count, say hello, pass X, count down, say bye, exit. But I specifically wanted to make it so that it reads English left to right as a literary abstraction here.
Let's move on. All right. I like it, though. This is the declarative version. I actually wouldn't call this subdivided.
There's a lot of ways to declare things, but I'm going to still call it subdivided.
All right.
But this is one subdivided version. There is a second subdivided version. So notice this one is sub-func, subdivided into functions. The next one is that.
Subdivided into combinators?
Subdivided using combinators. These are functions, but they don't have the structure of the direct function block. There are no function arguments in here. Notice there are no X's anywhere in there, or W's. This is completely free of argument names. There are only function names. Whatever arguments come in from the right or left and somehow implicitly passing them along to where they need to go. This is combinatory logic, which BQN supports very well. Look at the bottom line. It's almost identical, right?
Yeah, I see that.
So what do you see as a difference?
The sideways T on the right. Oh, it doesn't have the block.
Right, so if you look at...
What's the significance of the parentheses? Look at valid input. Valid input has left brace followed by left paren followed by not empty plus caret, then only digits. I'm assuming the caret means that that's an and condition?
Yes. It'd be more readable if I put a space in there, huh?
And you have to put it in parentheses so that the value coming in is applied to both functions?
Let's look at it over here. It's almost exactly the same.
Except that the combinated value is coming in. All right, let's define combinator.
Okay, a combinator is a way of taking multiple functions and producing a new function that changes the way those functions are called, I guess is a description of it. Let's go to browse self. Combinatory logic, Connor's site. The combinators are required to do tacit programming. Transformations and functions that call other functions without naming parameters. These mechanisms describe ways the parameters can get passed in and reorganized into new functions. Let's actually show what it looks like in BQN. This chart in BQN is very useful. These are combinators. Instead of calling these functions separately or assigning to intermediate variables, for example, on the top here, you already recognize this one.
X into G and then the result into F.
That's the pipe.
Yes.
That is literally the pipe operator in Elixir, except that it goes from left to right instead of right to left.
Okay, what's the second one there?
You've got W and X going into G. So in this case, G is a dyadic function that takes its single result and passes it to a monadic F. In order to use piping in F sharp and Elixir, every function call has to be monadic, right?
Right.
Take a single argument.
That's not the case here.
You can have combinations of dyadics and monadics with different arrangements based on these different combinators. It's like having a bunch of different pipes with different bends in them, Y sections.
Okay, so you got over. That's not two arguments going into G. Explain that one to me.
This is G being called twice now. We're pre-processing both of these arguments with G separately, and those two separate results from G are passed dyadically to F. So notice the difference in a top, G is dyadic, F is monadic. In over, G is monadic and F is dyadic. What's same is that G is a pre-processing of the arguments before F gets the result.
I think is probably challenging for people that are coming from the imperative programming world is to understand when you come into array programming, you're dealing with these concepts of monadic and dyadic operators or functions because there's only monadic or dyadic.
In these array languages, yes, although J actually does allow three. It allows an X, Y, and Z in some cases. But APL and BQN strictly are single argument or two arguments. That's it. If you want more, you've got to combine your arguments into a list and then pull the list apart inside your implementation.
In the over, what's the difference between the over on the left and the left on the top?
None. If both functions are monadic, the result is the pipe in both cases.
Okay.
It only changes meaning when you have a dyadic function. In the case of a top, your G is dyadic. In the case of the over, your F is dyadic. If you call them monadically, functions can be ambivalent. You have a mode where it takes one argument and a mode where it takes two arguments.
What about constant?
Whatever F is, it's F. If I give it two arguments, the arguments go nowhere.
Okay. Looking at the before, the first one is easy to understand.
You've seen that because we used it a lot.
Right. So we're going to pass X into F and pass the result to G.
Not only that,
X is going to be passed to G as well.
F's result becomes G's W.
Yeah.
Why it's called before is the function on the left, F, is always evaluated first.
Right.
If you look at after, you see that F is evaluated after G. The circle with the line points at the one that gets evaluated first.
What does this swap mean?
Swap your arguments. They're on the wrong side. Just flip them.
If you only pass one in, then you're just going to get one back.
This would actually act as the W combinator, which would double it. F is dyadic, and you don't provide W, it gets doubled. These correspond to different combinators. This swap here corresponds to the C combinator. K is constant, I is identity, B is the single pipe, B1 is two arguments become one. What Connor has done here is he shows you the equivalent features in the languages for these particular combinators. So there's BQN here, and you can see there's some that are supported and some that are not. Here's what it looks like in APL. Here's what it looks like in Haskell. And at some point, maybe we'll add WeWa. WeWa supposedly has a lot of combinators. But yeah, has your brain exploded yet?
Not yet. Let's go back to the code, though.
Okay.
Have we defined what a combinator is?
A combinator is a way of changing the invocation of functions by creating new functions.
Right.
It may alter the order and the organization of arguments and results from those functions. I don't know if that's official, but that's my definition.
Combining functions in different ways. That's what a combinator does.
So think about this as a compiler, interpreter, implementer. In fact, you can write combinators in an imperative language that has functions as first-class values, right? C++ supports it now, Rust supports it, Kotlin. You can write combinators. In fact, I did that in Scheme because you can pass a function as a value. A simple way of thinking about combinators is they always take functions and they produce a new function.
Right.
Here's these functions that this takes one argument and this takes two arguments. I need to make a new function that would take those and give you the result as if you called those in this order, and I'm going to give you a function that you can then call to do it. It's not the actual execution of the function, it's the definition of the function. Then when you apply the combinator, it's like applying the call of the function. You're calling into a function that calls another function that calls another function, but it's all been wrapped up for you in a single package. Is that making any sense?
In a word, no, not really. I think maybe the best way to explain combinators is probably like you just did a little while ago with the examples, with the top and the before and the after, because it's a hard thing to explain.
We're going to have to make combinators its own topic. Let's just be satisfied with scratching the surface. There's ways to do combinators in both APL, J, and BQN with symbols. That's the after. This is the before. This is called choose. This is a way of doing an if. But also, if you put three functions in a set of parentheses, it's a special parsing rule. This and is an operator that's built in, and these are two functions that I've defined. This is a fork. I talked about forks a little bit in J. This particular one is the phi combinator. This is so commonly used, and it's easy to express them this way. It's a standard that's done in J and APL and BQN. This one says, give me whatever argument that's coming in, pass it to this fork, calls not empty monadically, calls only digits monadically, takes the result of both of those,
Passes that into 8.
arguments to the and. That's effectively your this and this. But we talked before about the short circuiting. This does not short circuit. It can't, right? It's not going to evaluate the and until it also evaluates the only digits. If we wanted a short-circuited AND, we'd have to create that. I don't think BQN has a short-circuited AND.
Of course, it's not going to be short-circuited because it's going to pass them both in. I think I've just figured it out. A combinator is something that combines the function of multiple functions. In other words, it combines what multiple functions do together. Go back to Connor's show of the different combinators.
Yeah.
Talk about here over on function abstraction. Help us understand. The first one's got A dot A. What does that mean?
This says, given A, the result will be A.
That's what I thought. And then you've got another one that says, given A and B, the result will be A.
Yeah, if you give me B applied to A, I'm going to give you A.
And the next one is going, if you give me a B applied to A, then I'm going to give you B.
Yes. This is lambda calculus notation. This is Alonzo Church notation. It's its own thing. The SKI and the SK is another way of saying the same things in another notation. And then over here, you have the actual syntax from languages that support it. Haskell uses words like id, const, join, flip. It uses a few symbols, like the dot operator is their version of the pipe. If we were to show F sharp, we'd see pipe under here for B. For Elixir, we'd see pipe.
And Connor did all this?
Oh, yeah. He is the combinator king. If you really want to know what's going on, watch this. He actually shows you how this works in C++ and Python and stuff like that. It's a lot easier to understand watching this video. So combinatorylogic.com, go there, watch the video. It's amazing. As we go back to code, it's not truly tacit because I have named functions here.
Still declarative.
Totally declarative. Well, the last thing is imperative, but everything before it is declarative.
Ultimately, I think you have to have, in any language, imperatively say what you want to do.
Yeah, you have to at least say run. Do something.
Onward.
This is BBHW-golf. So this is fewest number of characters possible.
Mm-hmm.
So you can see I assign these words that are kind of long to single variables just to shorten it. Totally unreadable golfing code. It's not tacit. It has X parameters in it. Everywhere I see a repetition of a bunch of characters and I can shorten it, I did that. So you can see there's the F, there's the O, there's the C. And in golf, the carriage returns count, but the carriage return takes the same amount of space as a diamond. For readability, I at least separated the carriage return instead of using the diamond. But on the next one, I didn't use carriage returns, and it is the one line.
Okay.
So carriage returns are gone. Everything's separated by diamonds. It's the same code as the golf. Every character is necessary in this implementation. Could it be golf to even shorter? Probably, but this is my first one, and the total character count is 300. The final one is not golf, but you'll probably find it pretty unreadable. This is fully tacit. There are no intermediate function names. There are no intermediate variable names. It's all combinators. This program can be written tacitly, and this is one way to do it. There's probably ways to get rid of some of these boundary characters, but I wasn't even able to achieve that yet in J. Remember, I did J and I was making it tacit, but there were still some X's and Y's in there. There were still some argument names. This I just finished before we started. I finally got rid of all the argument names, all the function names, all the variable names, still immutable, pure tacit. And by your definition, probably purely unreadable.
Anything written tacitly is immutable. Isn't that true? There's no intermediate variables.
This is the first thing I've accomplished so far, pure tacit code for BBHW.
Does it work?
It does work perfectly.
Let's see it.
Well, you don't believe me?
We haven't actually seen anything run yet.
No, I did it, just we didn't talk about it, but I was typing it while you were doing something else.
I don't believe you. I want to see this one run.
I do have run tacit. Just for proof, run tacit calls BBHW tacit.
Okay.
BBHW tacit.BQN is that. It's the one we just looked at.
Okay. So run it.
Run tacit. Countdown. Frog. Dog. Cat. Space. By the way, if I put a tab in there, it's not treating as white space. It's only trimming out the blanks. But if I do this.
In mine, I don't trim out the blanks at all. If you put in a space, it'll tell you invalid countdown.
And then, of course, if we do 3, we get 3, 2, 1. So, yeah, it works, dude.
All right. Congratulations.
That was hard. And in fact, just like in Scheme, doing the subdivided ones first, where I did break it out mentally into abstractions, was helpful in getting rid of mutation, getting rid of ultimately intermediate variables, because you can see in the previous ones, this is the default. And until somebody says do it differently, we'll keep this as the default.
I would call the first one the most idiomatic.
Yeah, that's the goal. And it's the one where I actually keep the symbols in there. And then this is subdivided functions, subdivided combinators, golf multi-line, golf one line, fully tacit.
Right.
That was fun. And I learned a lot about BQN. I spent about a week going through these variations and writing this. But the main goal, get rid of that mutation. Getting rid of global variables was less of a goal, but the primary goal was we need to get rid of mutation. There's got to be a way to do it. And we could see in all these ways, they all solve that problem. They have side effects. They're not pure functions. The only pure functions here would be, like you said, only digits, valid input.
I mean, when you work so hard programming tacitly or even idiomatically, when I say idiomatic, the more natural way to program in that language. Is that your thinking as well?
Yeah, I agree. It just depends on defining some group or some person as who makes that determination.
I think it's natural to say that would be the language authors. When they wrote something, they intended it to be used a certain way.
Well, languages that have been around a long time, in some cases, the community of programmers that depend on the language and write production code in it may have something strong to say that disagrees with the original author of it. Would you say the way JavaScript is idiomatically used today matches the original intention of Brendan Eich when he wrote it as a scripting language for a browser?
Your point is well taken. Maybe what we mean is the authors plural. The authors for whatever version of that language that you're using, right? So what we think of as the natural way to program in that language that mostly supports the intent of whatever version you're using.
I agree with that definition, but as I point out, it depends on someone or some group representing an authoritative voice to make that definition. We do have language creators that change their mind and later on will say, that was a mistake, I shouldn't have done that. And so you have to get a fresh perspective from them and say, okay, well, how should we do it now? Even though the language supports that old way.
I hate it when they don't get it right the first time. I mean, I don't understand.
Unfortunately, Ken Iverson is no longer with us on APL, but I would say Adam Brodevsky manifests the spirit of what's good about APL and how to use it right. And the fact that he just thinks in APL, not even translating it to whatever language he speaks, is definitely an advantage.
Getting back to when we talk about functional programming or tacit programming, when I think of idiomatic programming, I think of something that is going to be readily understandable and something that can be refactored in a reasonably efficient way. There's a breaking point somewhere where something becomes too declarative or too functional or too tacit that makes it so that it actually becomes harder. A good example would be your golf version. It would be great for trying to make something really small to maybe win an award in code golf, but is it practical to code that way and then to be something that's going to grow and change over time as it's used? One example where you really don't have any choice, like if you had to code something in 4K, well, you didn't have the freedom of action that you have languages now, where you can write totally declaratively, or you can write something really, really small. If you had to be caught in 4K, you'd have to write in the golf fashion, as small a code as you possibly could. But in the world we live in today, is there a point in which something becomes not worth the carrot? Or the way you like to put it, the juice is not worth the squeeze. To work that hard to make it tacit, to make it functional, to make it declarative, when it becomes so much harder to maintain over time?
It depends on the platform. Desktop computer, we got lots of memory, we got lots of space, we got lots of screen real estate. We can do things we couldn't do, and that's evolved over time, to your point. And in some ways, you're the best person to speak to this because you went to programming in hex, not even assembly mnemonics, but you had to know the actual hexadecimal code for each machine language operation, and you had to write your code in these numbers. I worked on an operating system in assembler, but I was using macro assembler with at least mnemonics, move, sub, shift, things like that. One case in not too far recent past where this has come up for me is in shader programming. Code that actually run inside a GPU as efficiently with the least amount of instructions. No branching is allowed. So the idea of using Boolean masks and the things that sort of happen in these array languages fit really well into shader logic because they have to work parallel. There's no variable mutation. You can't do any of that. And you definitely want as few instructions as you can. Now, do you write it in a very cryptic, symbolic way? No, there's still keywords and stuff like that. But it does get compiled down into shader instructions and a shader language, which is very terse in its design and implementation. I think it's gotten bigger over time. So it depends on the platform. If you're doing something inside a little robot that's got an Arduino in it or even a Raspberry Pi, it changes the forces acting on you, thus changing your priorities and how you're going to write code. For Go Golf, the goal here is just the fewest strokes possible. It's not practical other than accomplishing that goal.
When you're looking at open source stuff, there are actually a lot of things that are written well. But a lot of the time, it just seems like the attitude is when in doubt, add more code. Just code and code and code and code and code and code and code. Everybody loves to code. Just keep writing more.
Isn't that the entire software industry? When in doubt, add more code?
Right. For me, it's not the competition. It is to write less code, but to write the best code. Write the most efficient code, the most effective, the easiest to understand, the easiest to modify and maintain. That is a key, especially when the requirement is not for things to work. The requirement is for things to get released, because you're going to be fixing problems all the time. You're going to be dealing not only with the fact that it was broken when you released it, and new requirements came in after that. So in that world, reliability and maintainability, not writing the tightest, although small bits of code are good. If you're going to write something really small, then make sure it does something really small. If it's got too many functions, too many inputs, too many outputs, too many responsibilities, then make it big enough so that you can clearly understand what it's doing. When it comes to coding tight, I think there's a trade-off somewhere. I often fall back on dry because that's the one that's bitten me most of my career. I'm trying to get into what you like to do, writing 4 or 5 different versions of something that does the same thing. I think I'm going to be better at this if I do more of that, like you've been doing.
Building systems. The fun part is how I build them as well as I can. There's an outer problem, and software is a tool to solve that outer problem. As a servant to people that paying me to do work, solve their outer problem, trying to make the software that they need to do that as good as it can be. But in the end, like you say, the priority in most of the projects we work on is get something released. You say that maintenance is a priority. Well, it's rarely a priority of the businesses. It becomes something they end up having to stumble over and at some point can burn them down to the ground if they don't address it. But to them, it's overhead, it's a cost. It's not the goal. The goal is to get this functioning thing out there and to make enough money, please enough people. As a builder of things, my goal is to
build it the best.
And that is self-serving to some degree because there is a time and effort cost. Enable that by developing better skills so that those things happen more automatically. Develop better practices that become reflexive. Proglang base and proglangcast is a way for us to do this exploration. But when it comes down to solving problems for somebody or maybe even to myself, I do want to have a short stack.
What have you found so far that you prefer for something like doing Proglang base?
Erlang and BQN.
You want to use BQN?
There's so many things I like about BQN.
As we get more into the array programming, I want to get better understanding. When I was doing APL years ago, it was really doing data processing. We're going to be doing data mining with Proglang base. So I guess it makes sense. That's why I asked about this combinatory logic that Connor did. I want to understand a little bit more about it and what the notations are. I get what lambdas are, but there's a way that they're thought of in the industry and where they come from, and I want to understand that better.
I think it'd be great for you to do Weewa for a couple of reasons. One, it's stack-based, which you already have experience thinking in a stack way. Remember, you said that back in the previous episodes, that prefix and postfix does not bother you. It's very strong in support of combinators. And I could be wrong, but I believe he said that it supports more combinators than BQN does. So I think it'd be great for you to try it and see how it goes. I'm still going to do K. But I wanted to come back to BQN, solve the mutation problem, get a handle on that, and then hopefully just be able to translate those solutions to K because it's a similar language.
Yeah, I want to solve the mutation problem in Common Lisp too. I intentionally did not look at the work you did in Scheme, and I want to do LFE, and so I don't know how quickly I'll get to Weewa, but I am actually very interested in taking a look at it. Are any of them more efficient than the other? Marshall has moved on from BQN now?
He wrote Singeli to BQN to make BQN's implementation faster. So CBQN by Zema uses Singeli. It's kind of bootstrappy. I really like languages that are built upon themselves as much as possible.
Yeah, no, I get that.
The reason I'm leaning towards BQN is it does feel to me like an evolution beyond APL and J. It does take care of some of the weaknesses. It has lexical scoping. Like you saw, I can be very functional in my programming style. Aside from that, the CBQN implementation, it's very small, very fast. You only need a C compiler. I've built it on all platforms successfully without a lot of effort. I've already started using it as scripting because it's quick and it's lightweight. I replaced bash scripts with it. I like the language and the implementation. It's a winner on both sides. But
All right.
it's good enough for us. That's all I have to say for everybody out there when you're dealing with arrays and symbols and tacit and not tacit and functions and combinators. I wish you all the best of luck.
Good luck.
Bye-bye.